Okay, so I'm now recording. So we're doing something called the chain rule. And I'll minimize these windows here so no one's, if you don't want to be in the recording. So the chain rule gives us more power when it comes to taking derivatives. It enables us to take derivatives of a whole slew of functions, and very complex ones too. So it's just giving us a little bit more flexibility with what we can do with calculus. So let's start with something simple that you guys should know, like y equals x cubed. You just do the power rule, right? It's easy peasy, right? Just move 3 to the front, drop the exponent by 1. There you go. Super easy, right? Now, what if you ask you to find a derivative of this? And let me change colors so it stands out. So of this, right? Or of this. Or something really weird like that, right? Because if you think about what does that mean? That means x to the 5th plus 2 times x to the 5th plus 2 times x to the 5th plus 2. That's just a lot of x to the 5th plus 2s. And if you wanted to FOIL all that, knock yourself out, and then do your power rule, but that's not terribly efficient. So let's look at this again. Y equals x to the 5th raised to the 3rd power. Now, of course, I know that's x to the 15th power, right? If I know my properties of exponents. And using the power rule, easy, right? 15 times x to the 4. So there you go. That's my derivative, right? Not that bad. Well, here's another pathway.
Mr. E.
Yeah, go ahead.
Why is it 15x to the 4th and not 15x?
Oh, x to the 14th. My bad. Sorry. You're absolutely correct. My apologies. It is 15x to the 14th. Wow, I can't believe I did that. Thank you for correcting me. Now, so what's happening over here? Let's talk about what's happening here. Well, again, first off, y equals x to the 15th power. The derivative was 15x to the 14th. Sorry, 15 times x to the 14th. So that was my apology that I messed that one up earlier. But what if I tried doing the power rule with this? What if I tried moving the 3 to the front and dropping that by 1 and saying, oh yeah, it's 3 times x to the 5th raised to the 2nd power. So basically what I just did was I tried to do the power rule for this. I tried to move the 3 to the front and drop this by 1. So I said 3 times x to the 5th raised to the 2nd power. Here's the dilemma. That equals 3 times x to the 10th power, which is not the same as this. I know this is true. I know that x to the 5th raised to the 3rd is x to the 15th, and the derivative that's 15x to the 14th. I know that's true. If I tried doing a power rule by keeping the parentheses intact and say, oh, let's move that 3 to the front and drop that by 1, I get 3 times x to the 10th. So that's not a true statement. Derivative of y is not going to be 3 times parentheses x to the 5th raised to the 2nd power. So that's kind of weird, right? Like, let's look at another one. Let's look at y equals x to the 5th plus 2 raised to the 3rd power. So some students who don't know their calculus well, or who conflate things, will say, oh yeah, let's move that 3 to the front, and let's drop the exponent by 2 and call it a day. And they'll leave their answer like that. That is not true. That is very, very bad. Now, let's do this. Let's expand this first. I know it's going to be a pain in the ass to FOIL, but I'm just going to do it. And I'll just tell you right now what it is. It's just going to be x to the 15th plus 6x to the 10th. Just trust me. This is what it is when it's expanded. Plus 12x5 plus 8. So that's what y equals. And my derivative is easy, right? 15x to the 14th plus 60x to the 9th plus 60x to the 4th. And of course, derivative is 0, right? So yeah, that's what we got. Now, what if I were to factor stuff out? Just let's say you felt like doing that. You don't have to, but let's just say you did. So if you just go into a step further and factor stuff out, then I'll get this. And apparently, I can factor this even further. Oh, sorry, x to the 14. I don't know why I like, no, it is x to the 4th, sorry. Okay. So 15 x to the 4, and then this can actually factor further as x to the 5th plus 2 times x to the 5th plus 2. Well, here's where it gets really, really interesting. That also could be written like this. 15 I know is 3 times 5, right? So I can write it like this. 3 times x to the 5th plus 2 squared times 5x to the 4, right? 15 breaks apart as 3 and 5, so I have 5x4, of course, and 3 I just multiplied to x to the 5th plus 2 squared. Now, this brings us to something pretty important, and it's called the chain rule. Because if we think about it, 5x to the 4, let me erase this because it's a little confusing. Let me erase all this here. 5x to the 4 is a derivative of x to the 5th plus 2. That's not a coincidence. So what did I just do? Or what could we do? See, I know this is not true. I can't just move that 3 to the front, drop it by 1. But what if I did that in addition to something else? So again, x to the 5th plus 2 raised to the 3rd power. Let's move that 3 to the front. Drop the exponent by 1. And then multiply by the derivative of the inside. Then you get this. Which is exactly what we got if we decide to expand this whole thing, do the power rule, and then do some fancy factoring. So this opens up some possibilities for us. We no longer need to FOIL a bunch of stuff and do a power rule. We could just do something called the chain rule. The chain rule is described down below. It's a little confusing, so let me kind of give you a better way of thinking about it. It's essentially this. The derivative of the outside times the derivative of the inside. However, the outside is going to be a composite function. So what we're told here is that y is f of u and u is g of s. So u is the inside. This is the inside. Y is the outside. So u is inside of y. So if you take the derivative of y with respect to u and the derivative of u with respect to x, apparently these cancel, and that gets you dy dx. Or essentially what you're doing is that you're taking the derivative of y, but keeping this intact, and then multiply the derivative of the outside. So like in this case, y equals u cubed, I know the derivative of that's going to be 3u squared, and u is x to the 5th plus 2, because y was originally this. So yeah, 3 times x to the 5th plus 2 squared. However, multiplied by u prime. And u prime, because u equals x to the 5th plus 2, u prime is 5x4. And you just slap them together. And that's your answer. It might be hard to see it that way. So really just think of it like this. This is how I tend to see it. Move that to the front, drop it by 1. So you could do that. However, you must multiply by the derivative of your inside function. Our inside function is x to the 5th plus 2. So we must multiply by the derivative of x to the 5th plus 2. And that is the chain rule. It's going to take some practice. it's a little bit confusing at first, but trust me, all my students they always get the hang of it. So let's try this for some other problems, and then let's verify using the calculator, make sure we're doing it correctly. So you might have questions. Hold on to your questions for now. Let's try the examples on this page, and maybe that might clear up your questions. So what I'm going to do is I'm just going to approach this, not using the whole, I'll be honest, I don't like this, the dy, du, du, dx. I think that's a little confusing. I'm just going to do this. I'm going to move my 5 to the front, drop this by 1. So y equals 5, 4x cubed plus 5x squared raised to the 4 power times, and I'll change colors, the derivative of the inside. My inside is 4x cubed plus 5x squared. And I'll do a little accent mark to show that I'm taking a derivative. So essentially, this is a composite function, right? You know, you could say one function, we'll say f of x is 4x cubed, or let's say f of x is at x squared, and g of x is 4x cubed plus 5x squared. Sorry, I meant to say fx to the 5th power, my bad. Say fx to the 5th power, and g of x is 4x cubed plus 5x squared. So f of g of x is 4x cubed plus 5x squared to the 5th power. And what you're doing the chain rules, you're doing the derivative of a composite function. And so essentially, that's what's happening. You're taking the derivative of the outside, keeping the inside intact, times the derivative of the inside. So if I work this out, sorry, and that should be the derivative, my bad. So y prime is going to be 5, 4x cubed plus 5x squared raised to the 4 power times the derivative of the inside, which is going to be 12x squared plus 10x. And leave your answer like that. Don't go any further, please. You're going to drive yourself insane if you do. Leave it like that. That's totally fine. So let's try this again. Let's look at example 2. And let me change to a different color here. So y prime is going to be the derivative cosine, which is negative sine, 5x, times the derivative of the inside, like that. So it's a composite function. 5x is your inside, cosine is your outside. The derivative of cosine is negative sine, keep the inside intact, but then times the derivative of the inside. And if you do that correctly, you should get negative 5 times sine 5x. Okay, let's look at example 3. My derivative will be 3 root x plus 1 over x raised to the 2nd power. So essentially, we start humming along here. Times the derivative of the inside, which will be root x plus, I'll say x to the negative 1 power. So I'm gonna, just make it easier. Derivative. Let's keep moving here. And let's switch that back to green again. That one's kind of weird. That's 1 over 2 root x. We kind of know that already from a previous unit. Or you could do like x to the 1/2, move the 1/2 to the front, drop by 1. That's fine. And of course, it's minus x to the negative 2 power. And leave your answer like that. Please, please, please do not go any further than that. That'd be ludicrous. I don't expect you guys to simplify this stuff. So in essence, think of your overall equation as a composite function, and it's just f prime g of x and g prime of x. You have the outside, keep the inside intact or unchanged, times the inside. This is how we go about the chain rule. So now, let me field any questions. Are there any questions before we do the bottom of page 2 as well as page 3? Feel free to speak your microphone or put it in the chat. Any questions of what we've done so far before we do more practice problems? Nope. Okay. Let me do more examples. We'll end by the yeah. My hope is to get to the end of page 3 of these notes. I'll do a video on pages 4 and 5 later today. And then most likely on Tuesday, we'll probably do a breakout session and start a class just to practice more of these problems with chain rule. And probably we'll do a quiz next week also. Probably on next Thursday, I want to do a quiz. I'll put it as a Schoology assignment, just so I can make sure that you guys can show me that you're doing chain rule correctly, because it's very mechanical and kind of easy to mess up if you're a little careless. So, but let's keep going here. Okay. So for number 4, exam 4. Okay, so all I'm going to do is take the derivative of sine, which of course is cosine, 7x minus 1. And now I know I got to do the derivative of the inside, 7x minus 1 derivative, plus tangent 3x, I know derivative tangent secant squared, 3x squared, times the derivative of that. So that's going to be 7. So 7 times cos 7x minus 1. And of course, that's going to be 6x. 6x times secant squared, 3x squared. And leave your answer like that. Do not do anything more than that. Please, please, please. There's no need to simplify any further. I think what I might want to do is maybe I'll make these questions multiple choice questions, so you kind of know where to stop. That might be, because I've seen some people kind of just take this a little too far. So that might make, but I think what I'll probably do for our quiz is I might do something a little more intricate that might involve like product rule. And we'll practice that next Tuesday, because we'll have a quiz on Thursday of next week on chain rule. And I'll put that as a Schoology assignment. You know, so I can see some work. But here in this case, yeah, just stop there. I mean, you're good. There's no reason to go any further. Now, before I move on, if you think about it, you guys have been doing chain rule the whole time. For example, we have y equals root x. That's y equals parentheses x at a half power. What's that derivative? 1/2 times x to the negative half power times the derivative of the inside. My inside is just plain old x. What's the derivative of x? 1. Just 1. So in essence, you have been doing the chain rule the whole time. Just haven't realized it. So it's just 1/2 times 1 over root x times 1. So the chain rule has always been there for us. We just haven't realized until now. So if you want to always use chain rule the entire time for the rest of this class, yeah, go ahead. But when you have something as simple as root x, and you take the derivative of the inside, that's just going to be 1. Like, for example, y equals sine x. You know, I know that's cos x, but times the derivative of the inside, because the inside, of course, here is x. Well, guess what? Derivative of x is 1. So just cos x. So we actually have been using the chain rule the entire time, just we haven't realized it. Okay. Let me quickly do 5 and 6. And then I'll see if you guys can handle 7 on your own for a little bit. Now for number 5, we have a weird composite function. So, but again, you're outside. This is your outside. That's your inside, right? Derivative cosecant, we know, is a negative. Remember, if you have y equals cosecant x, or let me just do this. So that cheat sheet that I shared with you guys. It's already in Schoology now. These derivative, I would strongly recommend that you print and download this today or tomorrow or sometime this weekend, and have that available to you because it has all these rules here, and all these different formulas as well. So anyway, d dx of cosecant x is just negative cosecant x times cotan x. So when I do my derivative here, I'm going to do negative cosecant of, and it's really weird. So just bear with me for just a sec. So my inside's cot x. I'll take rid of that. And remember, you got to keep the inside intact when you do the chain rule. You got to keep the inside intact. I'm not sure if I spelled that correctly, but you got to keep it unchanged. So what am I going to put inside those parentheses there? Cotangent x. That was my input to begin with. That would not change. But my outside is cosecant. Derivative cosecant was negative cosecant x cotan x. Well, if I replace that x here with cot x, then guess what? Replace these x's here with cot x. So you got to keep that intact. But of course, derivative times derivative of the inside, which is cotangent x. So I'm not out of the woods yet. My final answer is negative cosecant of cotangent x times cotangent of cotangent x times derivative of cotangent, which was what was derivative of cotangent? Negative cosecant squared x. Yes. That's why that formula sheet is really going to help. You can leave your, and then you have two negatives, obviously, so they kind of cancel. So cosecant okay. So that's example 5. The more I've thought about now, I don't want to do example 7 with you guys because there's about 5 minutes left. That would not be doing it justice. We'll just talk about example 6. And it's actually kind of a nice midway point because I'm in the middle, right smack in the middle of these notes. So I did 2.5 pages with you guys today. So this will be our last one, example 6. And we'll talk about notation a little bit. Example 7 and 8, as well as pages 4 and 5, will be done as a video. Okay, so let's talk about example 6. Okay, so instead of x, we have theta, whoop-de-doo. It's totally arbitrary, have a different letter, who cares? Now remember, that's like saying r equals sine theta to the second power. We just get lazy. Mathematicians are very lazy, right? They just write, yeah, just put the square next to sine, it's good. Really, it's sine theta then squared. So remember to always rewrite. Whenever you see these things here, like sine squared x or cosine negative 3x, make sure you rewrite them, right? Very, very important. So I take my derivative, so r prime will be 2 sine theta, then times derivative of the inside. Remember, my inside was sine theta, so I got to take derivative of sine theta. And of course, that's just going to be r prime equals 2 times sine theta times cos theta, which is your final answer. Now, for those who might remember, that's actually an identity. It's a double angle formula. Sometimes the textbook gets kind of cute, and they'll actually put the answer like that. Don't worry if your answer doesn't quite match what they have in the textbook. They're just getting kind of cute and doing a trig identity. I don't care. The College Board does not care either, just so you know. So don't worry about that. One quick thing before we sign off, because it's we got about 2 or 3 minutes left. Now, yes, for heads up about notation, that is true. If you have sine to negative fifth x, it is sine x raised to negative fifth power. Totally true. This, however, is not true. If you're taking sine x raised to negative 1 power, that's just 1 over sine x or cosecant x, the reciprocal function. This right here is the inverse sine, which is a totally different thing. Remember, we do inverse sines. Like, remember back in the day when you had like a right triangle, so you knew all the sides of the triangle, say this was like 3, 4, 5, just totally making this up. You call theta, and you want to solve for theta. And we knew sine theta was like 3/5. And then if we want to solve for theta, we said theta equals inverse sine of 3/5. That helps us solve for angles. So an inverse sine is an inverse function, right? The input becomes the ratio size of the triangle, the output becomes the angle. The reverse of sine, which is when the input's the angle and the output's the ratio of sides. So we're going to explore derivative inverse functions much later. Well, not much later, I think next week. But make sure you don't confuse that. I think that's just one thing I want you guys to keep in mind. So yeah, I think that's a good place to stop now, because example 7-8 will take some time. Probably better to do as a video anyway. And then I'll give you guys some problems to do as well. So most likely I'll give you some problems from 4.1 and then maybe some from the chapter 3 review. And I did leave my textbook in the car, so I'll have to kind of take a look at that. And yeah, I think that's pretty much it. So, and there'll be a video on the rest of the 4.1 notes, and there'll be a Google form as well. So you'll have quite a bit of work to do. So let me go ahead and stop the recording.